All right, folks. So welcome to lecture 2. And today we are going to be, I expect a few more technical problems today than we had on Tuesday because I'm in CMU, not at home. Anyway, so the topics for today, we're going to be looking at what neural networks can represent and what are the restrictions in terms of depth, width, and activations. So here's a quick recap. Here's what we've seen so far. Neural networks have taken over all kinds of tasks in AI. They can do fancy things like recognize speech, caption images, play games, translate languages, generate, even hallucinate, drive cars, all of these fancy things. These were tasks that were assumed once to be purely in the human domain of expertise. And these days, neural networks can do that. So what are these neural networks? They're just functions. They're these boxes which take in some input, like a voice signal, and produce an output, like a transcription. So, but what are these functions? Here's what we saw. In a human being, those functions are being computed by the brain because these are basically intellectual activities. And so, in their basic form, the neural networks mimic the network structure of the brain. Now, the brain, as we saw, is composed of networks of neurons. Each neuron is a structure like this one to the left, which has a lot of incoming connections. If the combined cumulative incoming signals from other neurons exceed some threshold, the neuron fires. The output of the neuron, the signal from the neuron goes down this long leg into other neurons. And the brain itself is composed of a network of such neurons. And so our computational model of the brain is also a network of computational models of the neuron. The basic unit is the perceptron, which looks something like the figure to the left. It has a number of inputs, and it computes a weighted sum of these inputs. If the weighted sum exceeds a threshold, the neuron fires, otherwise it does not. So the perceptron itself, this basic unit, is what is called a threshold unit. If you're an electrical engineer, you're going to recognize this as a threshold gate. And the operation is like what is given in this equation here. You compute a weighted sum of the inputs, summation I, Wi, Xi, where the Xi's are the inputs and the Wi's are the weights. If this matches or exceeds a threshold T, the output of the neuron is 1, otherwise it is 0. And we can read write differently. We can say that the neuron first computes an affine function of the inputs. And does anybody remember what the difference between linear and affine is? Anyone?
Bias.
Just the bias term, right? So it's the weighted sum of the inputs plus a bias. If this affine function of the inputs is positive or non-negative, the neuron fires, otherwise the output is 0. So that's like saying I'm putting this affine function of the inputs through a threshold function, where the threshold function outputs a 1 if the input is non-negative and 0 otherwise. And we can replace the threshold function by some other form of function. The basic structure of the unit still remains the same. First, you compute an affine function of the inputs. Then you put this affine value z. So I'm always going to represent this affine function of the inputs by the symbol z. You put this affine value z through some function to produce the output of the perceptron. And if this function happens to be a sigmoid, the sigmoid would be a smooth version of a threshold. But you can also have other kinds of functions like a tan H out here, or these other other functions which we will call activations. So the function that operates on this affine value is what we will call an activation function. And we can have other kinds of activations on the affine value. For example, the rectified linear unit, which is this red line here, where the output is the same as the input if the input is positive and it's 0 otherwise. Or the soft plus, which is a smoother version of the ReLU. You can have other kinds of activations. For this lecture, we're going to largely continue assuming threshold gates, threshold activations, meaning this activation function over here is going to be this type, where the output is 1 if the input is positive and 0 otherwise. So here's your first poll. Let me release it. Yeah. 5 seconds, guys. Okay. I shall give you a couple more seconds. Okay, I'll end the poll here. To answer the question from Elias, we'll get to those kinds of things later. A tan h of a sigmoid is just another function, right? And we will see those later in the course. Anyway, so 3x plus 7y is a linear combination. It is not affine because, I mean, it's a linear combination. 3x plus 7y plus 4 is not a linear combination because it has a bias. 3x plus 7y is also an affine combination because a linear combination is a special case of an affine function where the bias is 0. And so obviously 3x plus 7y plus 4 is also an affine function of x and y. Anyway, continuing. Any questions, guys? Nope. Okay, so we're going to jump into the subject for today. So we also saw that for this entire model to work, we need a network of such units of perceptrons, what we called a multi-layer perceptron, where perceptrons compute outputs that go into other perceptrons. And so first, this entire the course itself is based on the concept of deep learning. And the fundamental concept behind deep learning is the notion of a deep network, a deep neural network. So what does it mean for a network to be deep? Does anyone want to take a guess?
Multiple layers.
Multiple layers. How many multiple?
I think it needs to have at least, well, there's an input layer and then a hidden layer and then an output layer. That would be deep.
No, that would not. The input layer has no, the input layer is, you're right, it's multiple layers, but the input layer is really just inputs. There are no neurons over there, right? So there's a formal definition of depth. Oh, good God. I cannot stand my computer. It's gone into this spinny. Are you guys seeing this spinning wheel? Oh yeah, okay. So yeah. So to understand what depth means, we have to refer to graphs. In any directed graph with source nodes and sink nodes, you're going to have paths from the source to the sink. The depth of the graph is the length of the longest path from source to sink. So for example, in this figure to the left, you have a path of length 1. This first node is the source, the second node is the sink. You have a path of length 1, but you also have a path of length 2. So the depth of this graph is 2. What is the depth of this graph to the right? Anyone? It's
3.
It's on the slide, right? It says depth is 3. So you have a path of length 1. You also have a path of length 2, but you have a path of length 3. The longest path is length 3, so the depth is 3. Now, when you have a neural network, you don't count the inputs. The inputs are the source. Then you have many neurons, and you have connections from the input to neuron to neuron to neuron all the way to the output. And so the depth of the network is the depth of the neurons in the output layer. So here at the output. So for example, over here, the outputs are all at the longest path to the outputs in this figure to the left is 3. So the depth of this network is 3. Here in this figure to the top, each box represents a layer of neurons, a set of neurons. And so over here, you have paths of length 2, but you also have a path of length 1. The depth of this network is 2. This one, what is the depth of this network? Anybody? Anyone?
4.
That's 4, right? So you know what the depth of a network is. So what is a deep network? A deep network is a network where the depth of the output neurons is greater than 2. So it has to be this one over here, the figure to the top. Is that a deep network?
No.
No, it's got the depth is only 2, right? But what about the one to the left?
Yes.
The depth is 3. That is a deep network. That's a formal definition. Now, I keep speaking of layers. Does anybody want to guess what a layer in a network is?
Nodes at the same depth.
Nodes at the same depth with respect to the input. Absolutely, right? So it doesn't matter how I draw this. Look at this figure over here. Over here, all of these red neurons have a depth of 1 with respect to the input. So these are the first layer. All of these green neurons, visually they are not in the same layer, right? But all of these green neurons have a depth of 2. So these green neurons are part of the second layer. What about these yellow neurons? Are they part of the second layer? Anyone?
No.
Why not?
Because if you see the black one is connected red, then green, and then yellow. So it's basically second
Absolutely.
layer.
So the yellow ones are depth 3 and the blue ones are are layer 3 and the blue neurons are layer 4. So you can see how the layers are counted. A layer consists of all of the neurons at the same depth with respect to the input. And a neural network is considered deep if the output layer is depth at least 3. Okay. Now going back to our problem. So we've defined a network, we've defined a multi-layer perceptron. We know what depth is, but what can the network compute? What kinds of input-output relationships can it model? Now, we've already seen that multi-layer perceptrons are universal Boolean functions. We know that they can model individual gates, so they can compose, because they can compose gates, they can compose any Boolean function, and therefore MLPs are universal Boolean functions, meaning given any Boolean function, I can design an MLP for it. We've also seen MLPs are universal classifiers. You give me a classification boundary, I can build you an MLP that approximates it to arbitrary precision. MLPs can compose real valued functions to arbitrary precision. But what are the limitations? So that's what we're going to cover. MLPs as universal Boolean functions and the need for depth. The MLPs as universal classifiers and the need for depth, and MLPs as universal approximators, and a discussion of optimal depth versus width. That final bullet, RBF networks, I won't cover it in class, it's on the slides. So let's look at this first. How well do MLPs model Boolean functions? Now, we've already seen that a perceptron can model any simple binary Boolean gate. So we saw in the last class that this guy is, what was this one? Anyone remember?
And
That's an AND, right? And this is a NOT, and this is
Or.
an OR, right? So this is an individual perceptron. But it turns out a perceptron is actually a far more powerful than that. And how powerful? Let me see this. Maybe I should. Yeah. Look at this one. This perceptron is going to fire if any of the first L inputs is a 1. This perceptron is going to fire only if all of the first L inputs are 1 and all of the remaining inputs are 0. So it's going to fire if we have this situation. Oh, come on. I'm supposed to be able to write. It's not doing that. Okay. Let me. Let me do this on a notebook. So I have, oh God, working on Power, Microsoft is I should have stayed at home. This is just a bad idea. Junk. Remind me not to come to school for the next class. Okay. What happens if all of the first L inputs are 1 and all of the remaining inputs are 0? What is the total input at the total weighted sum of inputs? Anyone?
0.
L, because the first L inputs are 1 and the remaining inputs are 0, right? So the total input is L. What happens if I flip any one of these inputs?
It'll be less than L.
It will be less than L, right? So if I use a threshold of L, this one is going to produce an output of 1 only when the first L inputs are 1 and the remaining inputs are 0. If any of these bits are flipped, then this is not going to output a 1. So this is what is called a universal AND gate. You can have a very specific combination of inputs that the network will fire in response to. And in response to any other combination of inputs, it will not fire. Now, here is another one. This perceptron will fire only if at least one of the first L bits is 1 or at least one of the remaining bits is 0. Now, to see how this is, let's look at the condition where this condition is not satisfied. When this condition is not satisfied, the first L bits are all 0, right? That means none of them are 1. And the remaining bits are all 1, which means none of them are 0. In that situation, what is the weighted sum coming in over here? Anyone? You have L minus N minus 1, N plus 1 of these guys, right? So actually, the negative of that, it is N minus L minus 1 of these guys, okay? And so the total sum that would come in is it right? I have to work it out. But this value, L minus N, is going to be what will happen if all of these are 1 and all of these are 0. Yeah, there are L minus N of these guys, right? So at that point, if any one of them flips, then the number is going to become L minus N plus 1. But then you want it to fire. So if I use a threshold of L minus N plus 1, it means that at least one of these guys is 1 or at least one of these guys is 0. So this is a universal OR function. I know I've got confusing, but is this making sense? Raise your hands if it is. Yeah. No, these are Boolean, so it's 0 or 1, right? The order, I can arrange it in any order, so the order doesn't matter. You can say, I want this one of this specific set of inputs to be 1, or one of this other specific set of inputs to be 0, right? So that's fine.
I'm sorry, can you repeat what that number in the circle means, L minus N plus 1?
So look at this. There are L of these red guys, so there are N minus L of these green guys, correct?
Yes.
Yeah. So if these guys are all 1, the green guys are 1 and the red guys are all 0, then because the weight is minus 1, you're going to get L minus N as the total input coming in, right?
Yeah.
That is the only condition under which it won't fire. If any one of the bits flips, then it's going to that sum is going to increment by at least 1.
Okay.
Correct? So which means that if at least one of these guys is 0 or at least one of these guys is 1, it will fire.
Okay.
Make sense?
Yeah.
Okay.
Thank you.
Here's something even more interesting. So I have N inputs. Under what condition will this perceptron fire? Anyone?
K or more fires.
If k or more inputs are 1, this will fire. This is a majority gate. This is what is called a generalized majority gate. So as you can see, a perceptron is far more powerful than a standard Boolean gate, which is what fooled Rosenblatt into thinking this could compute any Boolean function. A single perceptron could compute any Boolean function. But then we know that it cannot compute an XOR, right? So, yeah, Aditya, that's right? So this is a threshold gate and it's a majority gate, right? So we know that a simple perceptron cannot compute an XOR. In fact, to compute an XOR, we would need a network of such perceptrons. Two of these to compute X and Y and not X and not Y, or XOR Y and not X and not Y, and then AND the two. Or in fact, because a perceptron is actually more powerful than a standard Boolean gate, it turns out that you can compute an XOR using this 2 perceptron circuit. Now I will leave this. This was shown to me by Gerald Friedland. I will leave it to you guys to figure out why this works. It's beautiful, right? And if you can't get it, then I can explain it on Piazza. Anyway, so because they can compute Boolean functions, perceptrons can compute Boolean gates, MLPs, which are networks of perceptrons, can compute any Boolean function because they emulate individual gates. So MLPs are universal Boolean functions. But then, if you look at the MLP for this particular ugly function, it has 1, 2, 3 layers, right? Or more generally, you would expect it to have many, many layers. But if an MLP is a universal Boolean function, what is the minimum number of layers that the MLP must have in order to be able to compute any Boolean function? Does anyone want to guess? 2. It needs only 1 hidden layer. Why is that? Any Boolean function can be expressed as a truth table. So these are all the input bits. This is the output. The truth table simply represents the combination of inputs for which the output is 1, right? But once I have a truth table of this kind, I can write this as a disjunctive normal form. So the DNF formula has as many clauses as there are combinations of inputs for which the output is 1. Each clause encodes the combination of bits. So this first clause says x1 must be 0, x2 must be 0, x3 must be 1, x4 must be 1, x5 must be 0. In other words, not x1, not x2, x3, x4, not x5. Similarly, the second clause is not x1, x2, not x3, x4, x5. So corresponding to each one of these rows, we will have a clause, and the pluses represent OR. So if any one of these clauses holds, then the output is 1. So this truth table can be represented by this Boolean formula. But then now I can have one, because perceptrons are universal AND functions, I can have one perceptron for every one of these clauses, and then a final perceptron which performs an OR, and voila, I have my MLP that computes this Boolean function using only one hidden layer. In other words, because any truth table can be expressed in this manner, and any Boolean function is just a truth table, a one hidden layer MLP is in fact a universal Boolean function. But then, if I want to construct a Boolean function using just one hidden layer, what is the largest number of perceptrons required in that one hidden layer for an n input variable function? To understand that, let's look at something called Karnaugh Maps. How many of you have heard of Karnaugh Maps? Raise your hands. Several of you, right? So at least a third of you have raised, know what Karnaugh Maps are. Now, a Karnaugh Map is a topological way of representing input patterns. So this is a truth table, actually. This is a truth table over 4 variables, W, X, Y, and Z. The columns of the truth table represent YZ pattern 0, 1, 0, 0, 0, 1, 1, 1, and 1, 0. Observe that if you look at any two adjacent columns, they differ in only one bit. So In principle, this last column is rolling around and touching the first column because these two also differ in only one bit. The 4 rows represent the 4 combinations of WX 0, 0, 0, 1, 1, 1, and 1, 0. And again, any 2 rows differ in only one bit. So these 16 boxes represent all 16 combinations of these 4 input variables. The highlighted boxes represent the input combinations for which the output is 1. For the remaining boxes, the output is 0. And so, because there are 7 boxes for which the output is 1, if I do a naive DNF formula, the naive DNF formula is going to require 7 terms, 7 clauses. In other words, if I build a naive DNF formula and then build an MLP to model it, it will have 7 neurons in the hidden row. But then I can reduce it. How? I can group these 4 guys. And if you group these 4 guys, what you're observing is because all 4 of these are highlighted, it means that it doesn't matter what W and X are, so long as Y and Z are 0, 0, the output is always 1. That's a disjunctive normal form, which has this form, which is basically the ORs of ANDs. This is a DNF formula. Make sense? Yeah. I just took any 2 arbitrary. There were ones. There were 4 inputs. I took W and X as one set and Y and Z as another set. I might as well have done W, Y, and X. It doesn't matter. You're still going to get 16 squares, right? So, so disjunctive normal form, that's this form of function right here. That's what a DNF is, okay? Where each, you have these pluses represent ORs and each of these is ANDs. So all 4 Karnaugh cells could also have been mapped together. Visually, it was just less obvious. So now what happens is that because I could group these 4 together, these 4 boxes didn't need 4 clauses. I just had to have 1 clause, not Y, not Z. Similarly, I could group these 2 together. And amongst these 2, you're saying that so long as Y is 0 and W and X are 0 and 1, the value of Z doesn't matter, the output remains 1, right? So these 2 together give me not W, X, not Y. Similarly, I could group these 2 guys, and that's going to give me not X, Y, not Z. So where did you get DNF plus 2? I haven't mentioned DNF plus 2. You could group, yes, Randeep, you could group all 4. It was just visually less obvious, that's all. In fact, I can, the actual clause here is going to be only 2 terms. But that's not the point, right? The point is by being able to group these things together, I can reduce the number of clauses and make a much smaller DNF formula. And so this DNF formula, again, what is a DNF formula? It's a formula of this kind. And it's ORs of ANDs, right? Not Y and not Z, or not W, X, not Y, or not X, Y, not Z, right? So again, Mangalam, this is it. Because I grouped these 4, this entire group gave me only 1 clause. It just says that W and X don't matter. Y and Z have to be 0, 0. That's all, right? Similarly, if I group these 2, it says so long as W is 0, X is 0, and Y is 0, X is 1 and Y is 0, the output is 1. Right? You're reducing the number of clauses. Otherwise, if you didn't, you'd actually, okay. To answer your question, Shafin, what is the arrangement of 1s and 0s that simply cannot be reduced further? Yes, Patrick, it would. Can anybody tell me?
Chessboard or
Absolutely,
checkerboard?
right. Once I have a chessboard, I cannot reduce it for any further. And now, if I want to build a DNF formula for this, what is the number of clauses, minimum number of clauses the DNF formula would require? 8. So a 1 hidden layer MLP for this Boolean function is going to require at least 8 neurons in the hidden layer, right? Here is a 3-dimensional version of the Karnaugh map. And so now you have 6 variables, but this, because you have 6 variables, you have 64 combinations. So the cube has 64 squares, cubes, subcubes, and every alternate cube is a different color. how many neurons would I need in in the hidden layer in a one hidden layer MLP for this Boolean function? Anyone?
32.
32, right? In general, if I have n inputs, I'm going to require 2 raised to n minus 1 perceptrons in the hidden layer. This is exponential in n. So here's a poem. Wait, you should be getting the poem. So Karnaugh Maps here, I'm actually using, basically there are three. You have to, can somebody help those who are not getting the poll? Obviously, many of you are getting the poll. So just as we had a two-dimensional pattern with wx and yz, I can have a third dimension which says maybe AB, right? So thank you, Charlie. Yes, we will get to that. I'm going to end the poll. So hurry up, guys, 5 seconds. All right. So the correct answer is because there are 10 inputs. If you think of a checkerboard pattern, every alternate pattern is going to be a 1. So there are 2 raised to 10, 24 possible combinations, half of which are 1 and half are 0. So you will need, there are 512 combinations for which the output is 1. And so the neurons in the hidden layer, you will need 512 neurons in the hidden layer. Okay, so this one, I just drew this. So I have Wx over here, UV along this axis, and YZ along this axis. That's it. Now it's hard to visualize because it's like a 4-dimensional toroid, but this is for illustration. The key point is this. We are going to require 2 raised to n minus 1 perceptrons in the hidden layer for, yes, for if you want to build this with only one hidden layer. But how many units will we use if we use multiple hidden layers? And so just as Charlie mentioned, these are XORs, right? This first pattern is simply W XOR X, XOR Y, XOR Z. This is the XOR of 6 variables. So these two truth tables are basically just XORs. And we know that an XOR can be done with 3 or even 2 perceptrons, right? And so this thing, I can compose it in this manner. First, I do an XOR between W and X, then I XOR the result with Y, and then I XOR that result with Z. Each of these requires 3 neurons. And so this Boolean function can be computed using only 9 perceptrons. And maybe doesn't seem to have, don't seem to have won anything over just the more naive implementation of a one hidden layer network. But then you can see that over here. When I have 6 inputs, I can XOR U and V. So Canary, I had 10 inputs. So that means there were 24 combinations. Because only every alternate combination has an output of 1, there are 512 combinations for which you can get a 1. So Abuzar, how would you get this with 6 perceptrons? Are you speaking of this one or the previous one?
The previous one, the one which had
Yes,
9.
of course. This you can do with 6, right? If you use only the 2 perceptron XOR. But the point is this. So you're absolutely right. I'm just using the 3 version for the figure because it simplifies some things, as you'll see. The point here is that now I can do this with U XOR V, XOR that with W, XOR that with X, XOR that with Y, XOR that with Z, right? And so this one is only going to need 15 perceptrons. Or more generally, I'm going to need for the XOR of n variables, when I compose the network in this manner, I'm going to require 3 times n minus 1, or if you use the 2 neuron network, 2 times n minus 1 perceptrons. So if you look at the comparison, when I use a single hidden layer, I'm going to require 2 raised to n minus 1 in the hidden layer, plus the 1 final output perceptron. So if I do this with one hidden layer, the number of neurons required is exponential in n. On the other hand, if I do this deep and I compose my network in this manner, then every XOR requires only 3 perceptrons, or 2 if you use the 2 perceptron model, right? And so for every new variable that I've added, I just need one more XOR. And so this only requires 3 times n minus 1 perceptrons. So what was exponential in n when I had only one hidden layer became linear in n when I allowed the network to be deep. And now how deep should it get? For this, remember that XORs are associative, right? So I don't need to build a network like this. I can begin grouping things. Yeah, much lower computation, right? And much smaller circuits. So I can compute the first, I can XOR the first pair, the second pair, the third pair, the fourth pair. So I can XOR all of my inputs pairwise. Then I can XOR their results pairwise, and then I can XOR their results pairwise, and then I can finally XOR whatever remains. And so because at each point I'm grouping grouping pairs of variables, the number of such blocks is going to be log 2n. And within each block, you have 2 layers to compute the XOR. So I can do this entire circuit using as few as 2 times log n layers. This is the worst case. We're looking for Boolean functions, right? For XOR functions. But then we're speaking of, I'm taking the worst case to give you an idea of the importance of depth. And so by basically, I can compute this XOR. If I let the network go deep, then I just need 2 times log 2 of n layers. And the number of neurons I require is only going to be 2 times n minus 1 neurons, right? On the other hand, if I want only one hidden layer, it's going to be 2 raised to n minus 1 neurons. So what does this mean? Suppose I decide that I'm not going to allow you all of these layers. You are allowed to use at most 4 layers. If I put a cap on the number of layers, then here's what is going to happen. I'm going to use the first 2 layers to perform an XOR, but then after that, I still have only 2 layers left, and I must XOR n over 2 variables, right? So this now becomes exponential again in the size of the input, which means that if I put a cap on the number of layers in the network, then in order to compute the function accurately, I will need an exponential number of neurons in the circuit. Is this making sense?
Sorry, can you repeat that again?
Okay, so look at this, right? Suppose I said, now we know that if I allow 2 log 2 n layers, then I can do the whole thing with just 2 times n minus 1 neurons, correct? But then, or 3 times n minus 1 neurons, because each XOR is 3. But suppose I only permit you 4 layers. What that means is that after this point, I'm only allowed 2 more layers, correct?
Ah, okay.
Right? So that's going to be exponential in the number of values here.
Okay.
Right? And suddenly the circuit became exponential. So we could sanction. I'm just using 3 for illustration because the layers come out cleanly. That's all, right?
Okay.
So now the actual number of parameters in a network is not the number of neurons, it's the number of connections. Here, for example, there are 30 connections. This is the number that actually matters in software or hardware implementations. But networks that require an exponential number of neurons will require an exponential number of weights because each neuron gets at least 1 weight, right? So the logic still holds. And so deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if recast using 1 hidden layer. So Aniket, the number of layers became log n, the number of neurons became linear in n over here. So for each variable, as I XORed each variable to the previous result, I just needed 3 more neurons. So the actual number of neurons was 3 times n minus 1. And they could be arranged in as few as log 2n layers. But then if you go below log 2n layers, then the size of the circuit immediately becomes exponential, right? And so in summary, an MLP is a universal Boolean function, but it can only represent an input function if it is sufficiently wide, it is sufficiently deep, depth can be traded off for sometimes exponential growth of the width of the network, and the optimal width and depth of the width depend on the number of variables and the complexity of the Boolean function, the minimal number of terms in the DNF formula to represent it. So Zishan, what was the question? So Ranadeep, you're just sort of going way out, many lectures out. So Zishan, what was the question?
Hi, yeah, I'm just wondering, since you just mentioned actually the connection is the thing that store all of those information. So basically, for all those two models,
so the number of connections here and here is the same. That's correct, right?
Yeah.
All I'm saying is, what is the smallest number of layers that you can have?
Yeah,
and
that's it. Thank you.
Right. So we are saying that if you want the network to not become exponentially large, there's a minimal depth required before things explode, right? So what we've seen is that even a network with a single hidden layer is a universal Boolean machine, but single layer networks may require exponentially large numbers of perceptrons. Deeper networks may require far fewer neurons to express the same function. They could be exponentially smaller. So we've seen how this works for Boolean functions. Let's look at classifiers. So we have exactly. Shafran, that's correct, right? So now this is the MLP as a classifier. We saw that MLPs can have categorical outputs, operating over real inputs, and model complex decision boundaries. We saw, for example, that a single perceptron accepting real inputs basically computes this Heaviside function where there's a linear hyperplane, where on one side of the hyperplane, the output is 0, and on the other side, the output is 1. And we've already seen this in the last class. We also saw how these guys can actually be used to compute Boolean functions. In a Boolean function, the inputs can only be on these 4 dots. So if my perceptron had a boundary here, this is going to be an AND. If a perceptron had a boundary here, this is going to be a NOT. And Madhav, what you can conclude is that the optimal depth depends on the dimensionality of the input. That's all, right? Okay. Anyway, so now you can see why a single perceptron cannot model an XOR, right? Because an XOR has this kind of boundary required. The output is 1 for these 2 diagonal terms and 0 for these other 2 terms, 0, 0, and 1, 1. So if you want you want a network which has a 1, outputs a 1 in the purple band and 0 elsewhere. So you will need 2 boundaries, 2 perceptrons, one to capture the lower boundary, the other one to capture the upper boundary, and then you'll need to combine the 2. That's why we end up with a 3 perceptron circuit, right? So here's a poll. There's a Hongji, there's a poll icon on Zoom with 4 bars. Click on it. There's no time remaining, Tom. I'm just sort of I give you anything between 45 and 50 seconds and randomly decide because I run out of time, right? So Saharsh, take that on Piazza. That's a very nice question. I'm going to stop this poll, guys. The answer is true, right? So, okay. So any questions so far? Abuzar, as we saw, you can do it with one hidden neuron, but with the 2 neuron circuit, and you can see, and I'll explain why that works in Piazza, right? But then let's go back. So we saw that a perceptron captures linear decision boundaries. If you want a more complex decision boundary, we know how to do it. You would, like this pentagon, you would have one perceptron for every boundary, boundary of the pentagon, and then a final perceptron to AND the lot, and that is going to give you this pentagonal decision boundary. But then, once you know how to compose a pentagon, you can compose more complex decision boundaries. For example, if you want a network which outputs a 1 if the input is in the yellow region and 0 otherwise, you would have one subnetwork for the lower pentagon, another subnet, hemming. There's a lot more to it, just hang on, right? But yes, what we are saying is that there's a minimum depth. If you go below it, then you may end up the consequence on the number of neurons required may be non-linear. So anyway, so if you want to model this double pentagon, you're going to have one subnet for the first one, another one for the second one. You OR the two, and you're going to get this double pentagon decision boundary, right? And so now if I want to compose, I can use the same logic to compose very arbitrary complex decision boundaries like this one. All I would do, for example, if I wanted this decision boundary, is to split it into many little polygons. Then I would have one subnet for each polygon. I would OR the lot, and then I'm going to get this crazy looking decision boundary. But then here's my question. This model has 3 layers, right? It has 2 hidden layers. Can I do it with only 1 hidden layer? Let's actually take the simpler example. Can anybody take a guess as to how I can get this decision boundary using only 1 hidden layer? Anyone? One perceptron per edge. Triangles. Triangles are still going to give you 2 hidden layers, right? Threshold on the output, maybe you have to give up some, check every pixel. You cannot do this with non-convex shapes. Maiden, is that how you pronounce your name? You have it right, right? How do you pronounce this lady's name? M-E-D-H-N.
Medhen.
Medhen? Medhen?
Yes.
Yes. Did I get it right? Medhen? You're right. Absolutely. And to see how this is done, here's how you do it, right? So let's say I want to do a square decision boundary. Then I'm going to have 4 neurons in the first layer, right? Each of them is going to capture one of these boundaries. What is the sum of their outputs? The sum of their outputs is going to be 4 inside the diamond. It's going to be 3 in these yellow regions. It's going to be 2 in the white regions, right? So if you look at the sum of the outputs of these 4 neurons, that's going to look like this figure to the top right. Yeah. And now if I use a cutoff of 4, it's going to give me exactly this diamond as the decision boundary. Suppose I want a pentagon. Then the sum is going to be 5 inside the pentagon. It's going to be 4 in these triangles. It's going to be 3 in these regions. It's going to be 2 in these corner regions, right? So if you look at the sum of the outputs of these neurons, it's going to be like so. If I use a cutoff of 5, threshold of 5 in the output neuron, it's going to give me this pentagon. If I have a hexagon with 6 neurons in the first hidden layer, then this is what the sums are going to look like. It's going to be 6 in here. It's going to be 5 in these yellow regions. Now observe something that happened as I increase the number of sides. What is the area of the space where the sum is less than 4, but still high? What is the area of the space where the sum is 3, just below 4? Anyone? In this example. It's infinite, right? So, but then over here, It became finite. Here, it not only stayed finite, it became smaller and smaller and smaller. So now, why can you not compose this guy with one hidden layer using the naive method? What will happen is just outside this boundary, this lower pentagon is going to give you a sum of 4. This pentagon is going to give you a sum of 4. You may actually end up with a sum in some parts of the white region, which is higher than the sum in the yellow regions, which is why you can't do this naively, right? So, but over here, we're not speaking of learning, we're speaking of constructing it, composing it. We haven't yet got into learning. We are speaking of what you could do, right? Is the activation of the output neuron. The output neuron is, look at this, is going to be applying a threshold. It's going to compare it to 6 in this case, right? Or here, if I were trying to do a heptagon, this is what the sum would look like at the output neuron. If I use a threshold, then it's going to give me the heptagon. So Dan, what I mean by naively is if I just try to model these individual boundaries and then try to compose it in some manner, you're not going to be able to do it. Okay, that's what I mean by naive. Okay, so this is what the sum would look for a heptagon. Yeah, exactly. Here's what the sum would look if I had 16 sides. Here's what the sum would look if I had 64 sides. Here's what the sum would look if I had 1000 sides. This is, in general, as you keep increasing the number of sides, what you observe is that you get this region inside the polygon itself where the sum is n, where n is the number of sides in the polygon. Then you get this vast region of the space where the sum is n over 2. And then you get the intermediate regions where the sum slides from n to n over 2. And these guys are the problem, right? Because when I try to put two of these polygons together, then these regions where the sums for the individual polygons are not 1, their sums will cumulatively add up to something greater than n and cause problems. If I keep increasing the number of sides in the limit, here's what you're going to get. You're going to get a sum of exactly n in this central region, which is going to look more and more like a circle. Not very far from it, it's going to become n over 2. And between those two regions, as n increases, it's going to fall off very steeply from n to n over 2. In the limits, it's going to look something like this. So you can sort of visualize what happens when you have a very large number of, when you're trying to model a polygon with many sides in this manner. You're going to get the sum of the outputs of the first layer neurons is going to end up looking something like this cylinder with 1 inside there, with a sum of, with n inside in the circle or this polytope and n over 2 outside. So why are we composing these? Because now if I use a cutoff of n, I'm going to get a perfect circle. I can add a bias of minus n over 2. And now the sum is going to be n over 2 inside the circle and 0 outside. And so now if I use a threshold of n over 2, I'm going to get a circular decision boundary. But now, if I want a decision boundary which is 2 disconnected circles, here's what I would do. Because I'm going to have one set of neurons whose sum composes the first cylinder, whose height is n over 2 inside the circle and 0 outside. I'm going to have another set of neurons which composes the second cylinder, whose height is n over 2 inside this circle and 0 outside. If I sum their individual outputs, then the total sum is going to end up looking like 2 individual cylinders. I'm saying that both of these have the same number of neurons, right? So this guy is composing 1 cylinder, this guy is composing 1 cylinder, each of them has n neurons. You could have more, then the heights would be different. But we are doing this for both of the cylinders to have the same height. Okay. And now what happens is that if I use a threshold of n over 2, I'm going to get a decision boundary which is 2 disconnected circles. And the whole thing has been done using only 1 hidden layer. So, and the key to this was that I kept increasing the number of sides till even, how is the n/2 bias important in a circle? Because the n/2 bias makes the sum 0 outside. That way, these two cylinders won't interfere. Otherwise, the sums just keep adding up, right? So it keeps the height constant, n/2. If no, because it's going to remain two disconnected circles, because the sum of the two cylinders is going to be, the sum of these two subnets is going to be n/2 inside these two circles and 0 outside, almost exactly, right? Exactly. That's whoever pointed out this is how you would do it. If I want to do this using just one hidden layer, here's what I end up stuck with. I just fit an arbitrary number of circles. It's going to be an approximation. I can get more accurate approximations with greater number of smaller circles. I can achieve arbitrary precision, right? So MLPs can capture any classification boundary. Even a one hidden layer MLP can model any classification boundary, which means even one hidden layer MLPs are universal classifiers. But deeper networks can require far fewer neurons than shallow ones. Here, for example, if I decide to have only one hidden layer, I need infinite neurons. If I decide to allow 3 layers, 2 hidden layers, I get 12, right? So you can see how depth really, really matters. And now, the circles could overlap. It doesn't matter. You can do all sorts of things because it's just composition, right? The point is you're filling up the space with circles. You're going to need a very large number of these circles to compose the entire boundary. So,
Professor?
Yeah.
Can you explain once again where the n/2 values come from?
The n/2 value is because, remember, when we did these examples, the sum here was 4 inside the diamond. Most of the other region was 2, right? Here it was 5 and 2. It was 6 and 3, right?
Okay.
So as you keep going down, what will happen is that it's going to be n inside and n/2 outside.
So
if I add the bias, this n/2 becomes 0 and this becomes n/2. Make sense?
Okay. Yeah, I understand. Thank you, Professor.
Right. So the point is this, right? If I have too few layers, it's going to require too many neurons. Now let's look at a somewhat more realistic example. I'm going to look at this pattern, right? I want a checkerboard pattern for 2-dimensional inputs. I want the output to be 1 whenever the input is inside the yellow band and 0 outside, okay, in the gray bands. I can do this with 56 hidden neurons, 2 layers, 56 hidden neurons. If I did this with 1 hidden layer, a naive circuit we saw is going to take too many neurons in the hidden layer. So no, n is not arbitrary, right? The threshold was n/2 to get exactly the top. If you use a threshold larger than that, you're not going to get anything. It's going to, so here the threshold was n/2, right? Because the cylinder has a height of n/2, and everywhere else it's 0. You could have a threshold between 0 and n/2. That would work. Anyway, so why can't I do this with 56 hidden neurons in the hidden layer? Because there are 16 boundaries of this kind, right? So I need 16 neurons in the first layer to capture each of these 16 boundaries. And then I need 1 neuron for each of these yellow regions. So there are 40 of these yellow regions. So I can capture this decision boundary using 16 neurons in the first hidden layer, 40 in the second hidden layer, and a final R. So 57 total neurons, including the output neuron. But then if you go back and look at this guy, once I capture the lower layer, this is just an XOR pattern, right? It's just Y1 XOR Y2 XOR Y3, where the Ys are the outputs of the neurons that capture these individual lines. And so if I did this, instead of having one neuron for each of these boxes, if I saw this as an XOR over the lines, then there are 16 Ys, 16 lines. So there are 15 XORs in all. And each XOR can be done, we saw, with 2 neurons. So that's 15 times 2, 30, plus 16. So that's 46 neurons. You can do this whole thing with 46 neurons instead of 57 total neurons. That difference may not look like a large number. But then suppose I look at something more complex like this, and remember, real life patterns are going to be very, very complex, right? So this is two-dimensional. These are two-dimensional inputs. I want the network to output a 1 when the input is in the yellow regions, right? This has 64 basic linear feature detectors. There are 64 lines. And then there are 544 yellow boxes. And so I would need 64 neurons here, 544 neurons here, and 1 output neuron. So if I just did this using 2 hidden layers, I'd need 609 total neurons. But then again, this is an XOR, right? Over the lines. And if I do this with a 2-gate XOR circuit, I need the 64 first layer neurons to capture these lines. And the rest of it is just an XOR over 64 bits. And an XOR over 64 bits is going to be 63 times 2, which is 126 neurons. That's all it takes, plus the 64 neurons for the 64 lines. So if I did this with an XOR circuit, I don't need 608, 609 neurons. I could do this with 190 neurons. And as the dimensionality of the input and the pattern complexity increases, the difference between the deep network and the shallow network can increase tremendously. What is 2 gate? We saw that we can do an XOR with only 2 gates. Remember? Way back when. So is parallelization more over the width of a network than the depth, or is it the same? It's actually going to be more over the width of the network, but then the trade-off is not in your favor, right? The 64 is because this has 64 lines. Just as in this case, I had 16 lines and 40 boxes. Here I have 64 lines and 544 boxes. Does that answer your question? So I have 544 of these yellow regions. So the number of neurons required in a shallow network is potentially exponential. And so again, this, it's not simple. It's not as simple as a bias. The reality is, yes, you can also do this with 1 hidden layer, but if you actually, in this particular example, and so I actually have that on the slides, but the number of connections is still going to be much more than if you do the deep network. So this is an XOR pattern, right? This, if you can recognize this immediately as a checkerboard. This is an XOR pattern. So there are 64 lines. If you cross the first line but not the second line, the output will be 1. If you go along any line, as you keep moving, the output keeps flipping from 0 to 1 to 0 to 1. So that's an XOR. And so this ends, once you capture the 64 lines, this checkerboard pattern is actually an XOR over 64 bits. So 64-bit XOR requires 63 times 2 neurons. Right? So the number of neurons required in a shallow network is potentially exponential in the dimensionality of the input. Or alternately, I haven't gone into this in great detail, it's exponential in the number of statistically independent features. Parth, did that answer your question? Yeah. Now, one last bit. So we said this is about MLPs as classifiers, right? The output is 0 or 1. What about continuous valued functions? Actually, an XOR is not really the worst case bit. Worst case, it turns out that for the majority of Boolean functions, the circuit size is going to be exponential no matter what you do. But that's something we're not dealing with. We're willing to work with approximations. We have a link to Shannon's paper on this subject on the course page. So, and it's actually also there on the slides. Now, let's look at MLPs as continuous valued regression. We already saw that a simple 3-unit MLP with a summing output can generate this kind of a pulse waveform, where the output is going to be 0 if the input lies below some T1. It's going to be 1 between T1 and T2, and 0 outside, right? And once you can generate this kind of pulse, you can always use those little square waves, scale them to approximate any continuous valued function. But this is for scalar functions. How would this generalize to multidimensional functions where the input has multiple dimensions? Does anybody want to guess? Anyone want to guess how this would generalize if I wanted to have the input have more than one dimension? Voxel cylinder. Yes, Sandeep, you're absolutely right, right? This is going to be, you cannot do this with boxes. You're going to have all the standard interference issues. Here's what we're going to have to do. We're going to have to compose cylinders. Remember when we tried to compose boxes, the sum was not always 4 and 2 or 2 and 0. You had these intermediate places where the sum could be 3, and that caused problems. So first you compose a cylinder where the sum is n/2 inside the cylinder and 0 outside. And then if I have any kind of function, I can scale each of these cylinders to different heights and use that to approximate my continuous valued function. And so MLPs can actually approximate arbitrary functions in any number of dimensions, even with just one hidden layer, to arbitrary precision. So an MLP is a universal approximator. You give me a function, I can approximate it to the precision you want. And I can do that even with just one hidden layer. But if I have only one hidden layer, I'm going to need lots of neurons, right? So here's a poll. Let me share the poll, guys. Or close to. Right. Okay, I'm going to stop this in 10 seconds. I'm not getting any more responses, so I will stop, okay? And most of you said true. Some of you said false. Those of you who said false are right. Why? Because you cannot model it exactly. We just saw this, right? If you're going to be filling this up with cylinders, there's always going to be an error. So an infinitely close approximation is not exact. So what this means is you give me an error, I can give you an approximation that's smaller than the error, but there will always be an error. Exactly. So this is with threshold activations, regardless of the activation. We will get to that. Regardless of the activation, you're not going to be able to go to 0, right? I mean, you're not going to be able to guarantee that you will go to 0. For some cases you can, but not always, right? Now, fine, I'm going to spend the final 10 minutes discussing sufficient depth versus width. So the previous discussion showed that a single hidden layer MLP is a universal function approximator. It can approximate any function to arbitrary precision, but may require infinite neurons in the hidden layer. More generally, deeper networks will require far fewer neurons for the same approximation error, regardless of whether it's a Boolean function, a classifier, or a real valued function. But there are limitations. So what is the limitation? There's this thing called sufficiency of architecture, right? So we know that a network with 16 or more neurons in the first layer is capable of, I'm saying capable of, you're going to have to set the weights and everything else perfectly to actually model this function. But a network with 16 or more neurons in the first layer is capable of representing this function exactly, right? But then what would happen if I decided to use only 8 neurons in the first layer? Can I compensate for that? I'm going to have 8 I'm assuming threshold activation neurons. So if I have 8 threshold activation neurons in the first layer, how many of you think I can compensate for that by increasing the number of neurons in the second layer to say infinity? Raise your hand if you think I can compensate for it. Everybody is raising your hand. You guys are wrong, right? So let's see why. Can somebody tell me why this is not the case? Anyone? Exactly. So here's what happens. A network with only 8 threshold neurons in the first layer may capture these 8 boundaries, correct? So if you capture these 8 boundaries, by the time you get past the first layer, if you look at the output of the first layer, all it can tell you is whether you are in which of these 9 regions you are, but it will not tell you where you are within the region. That information has been lost. And therefore, at this point, you no longer have any information about these divisions along the other line, right? You simply cannot reconstruct it no matter how many neurons how many neurons you have in the layer, right? So if we use 2 neurons, thank you. So let's get to that. It's not just real valued outputs. There's a little more to it than that. You need the nonlinearity, right? So even if you claim that these 8 neurons caught these 8 boundaries, all it would tell you, the output of these neurons is only going to tell you which of these 25 regions the input is in. It won't tell you exactly where it is within each of the regions. Therefore, subsequent neurons cannot recover the information required to construct this complete pattern. So also, this is just for the first hidden layer, right? The same restriction applies to higher layers. Even if I have the full complement of 16 neurons over here, if I have fewer than 40 neurons in the second layer, there's no way I'm going to be able to construct this pattern using just one more layer. So basically, if I decide to have 2 layers, the first layer needs to be 16 units wide, and the second layer needs to be at least 40 units wide, or I won't be able to construct this pattern. So regardless of depth, every layer must be sufficiently wide in order to capture the function. And why is that? Why 40? Because we had 40 of these yellow regions, right? Now, why is that problem? The problem is because we use the threshold activation. Now, the threshold activation, as many of you pointed out, gates information. So it basically, if I have 4 neurons in the first layer, it's going to partition the input into some 5 regions of this kind. But within each region, you're not going to be able to distinguish between one point in the region and the other point in the region. So subsequent layers do not obtain enough information to partition this data further. So how would you solve this? Anyone want to guess? Anyone?
Do not use threshold activation, maybe.
Okay, but here is the key point. Do not use threshold activations is is the right answer, but there's a reason for this. And the reason is when I use a threshold activation, it doesn't tell you how far away you are from the boundary. It only tells you on which side of the boundary you lie, right? Now, suppose I replace this with a sigmoid. Now, the sigmoid is nice. If I use a continuous valued activation as opposed to a discontinuous activation, then it not only tells you on which side of the boundary you lie, the activation function, which I've tried to sort of illustrate over here by using two different colors on the two sides of the boundary, tells you how far away you are from the boundary. So this gradation information in the gradation of the activation carries information about the distance from the boundary. And once you have that information, subsequent layers can use that information because now you know where you are within these regions, and you can use that to construct the rest of the pattern. But then here's the thing, right? Even a sigmoid activation is not great. Why? A sigmoid activation saturates. So once you go more than, say, this distant from the boundary, it saturates, and increasing the value beyond this point doesn't really tell you whether you're going further away from the boundary or not. That information gets lost to within some numeric resolution because of the saturation. So ideally, you want activation functions that keep continuing to inform you how far you are from the boundary, no matter how far you go. And so the kind of activations that do that are the ReLU, but the ReLU activation gives that information only on one side of the boundary. You have the leaky ReLU, which is better, which not only captures the boundary, but on both sides of the boundary, it tells you how far away you are from the boundary. So you basically want continuous graded activations that give you information about the distance from the boundary. And once you have the information about distance from the boundary, subsequent layers can use this information to construct the pattern. So the problem with using identity activation is that what is the combination of two identity activations? The notion of a layer disappears. If I chain 5,000 identity activations, it's the same as one identity activation. So the notion of a layer disappears. You need the nonlinearity. So narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded, but will require greater depth to permit later layers to capture the patterns. It's cheaper to use the threshold, but it loses information, right? So the lessons we've learned so far are MLPs are universal function approximators. They can model any Boolean function, classification function, or regression. Deeper MLPs can achieve the same precision with far fewer neurons, but must still have sufficient capacity. The activations must pass information through. In spite of this, each layer must be sufficiently wide to convey all relevant information to subsequent layers. Here's a last poll, and then I have one more minute. So here's poll 5.
The poll disappeared.
It disappeared?
Yes, it showed again.
Where? Okay. I'm going to go maybe a minute over. So Sam, you have to click on the poll icon, I think. Guys, please update your Zoom because I'm using these polls, right? Please update your Zoom. I'll end the poll here because I need to complete the course, right? So here, lecture, but here it is. A network with an upper bound on layer width cannot model any function by making it sufficiently deep. I'll give you an example, right? Suppose your input is 2-dimensional and I have only one hidden neuron in the first layer. you've lost one dimension. There's nothing you can do to recover it regardless of the activation. So that's okay. Don't worry about it. Nobody had time to answer this poll. I'm running to the end of class. I'm not going to be counting it. Okay. So this was about a lesson. So even if you use a nonlinear activation, you need a minimum number of neurons in each layer. Nevertheless, networks with graded activation functions are more able to compensate for insufficient width through depth than those with threshold or saturating activations, which is why sigmoids are not great. Tanh-H's, once you go beyond a limit, are not great. We can always compensate for limits in the width and depth of the network by using more graded activations. No, you cannot, right? If I have a two-dimensional input and only one neuron in the first hidden layer, there's nothing I can do with the activation to recover the lost dimension. But then, for a given accuracy of modeling a function, networks with more graded activations will generally be smaller than those with less graded activations. This is a truth, okay? And so, again, there's this notion of a capacity of a network. There are very many definitions. There's the information or storage capacity, there's VC dimension, and it basically has to do with how well a network can model a function. A network with insufficient capacity cannot exactly model a function. That requires more than the capacity of the network itself, right? But can approximate it with error. And there's a lot of work in defining the capacity of a network. We won't get into it, but I was hoping Gerald Friedland could give a guest lecture, we will see. But here are the lessons for today. End of the lecture, we've seen MLPs are universal Boolean functions, universal classifiers, and universal function approximators. A single layer MLP can approximate anything to a single hidden layer MLP can approximate anything to arbitrary precision, but could be exponentially or even infinitely wide in its input size. In its input size, deeper MLPs can achieve the same precision with far fewer neurons. In other words, deeper networks are more expressive. More graded activation functions result in more expressive networks. So thanks for your patience. We've run 2 minutes over. Here is the look ahead for next class. We know MLPs can emulate any function. They know they can emulate any function. We will begin looking at how to make them emulate a specific desired function. That's what we call training an MLP. We will begin talking about training an MLP in the next class. Take questions for the next few minutes. Chinmay, what is the question?
So in the poll, the last option that we had was that with graded activations, the network will generally be smaller than the ones that do not have graded activations. So I do understand that with graded activation, it's possible that with fewer number of neurons, you might be able to represent the same information. But as a generalization, I'm not able to understand how that happens.
So think about this, right? So you can see the thing to compare is maybe the threshold, the ReLU versus the leaky ReLU, right?
Okay.
The ReLU does not tell you how far away you are from the boundary on the left-hand side. Correct?
Right. Yeah.
So how do you compensate for that? Now you will need two ReLUs, one looking to the right and one looking to the left, so that you can have information about both.
Right. Okay.
Right? The leaky ReLU got both of them in one shot.
Okay. So how does this pass on between the layers? So like, given that this happens using two neurons in the same layer, if you pass this on into depth, would that also make a difference?
So again, the point is that if I have information about the decision, so let's go back to this 4 boundary case, right? So in the 4 neuron case, in fact, I can go down to 2 neurons over here, and the 2 neurons are going to carry information. They're basically, all they're doing is distorting the axes, right?
Right.
So now it's like transferring, it's like distorting the input space and transferring the entire problem 1 layer down.
Correct.
Right? So I can make the network layers narrower, but suppose I have sufficient gradation, I haven't lost information. So it's like restating the problem from that point on, right? So so you're going to have depth from there.
Oh, okay. Right. That makes sense. Yeah. Thank you.
Professor, can I ask a quick question?
Yeah.
It seems like there's a trade-off between number of layers and also the number of neurons, right?
So the the width and the depth, yes.
Yes, and I think you mentioned previously in cases where we have to be limited by the number of depth of the layer. When would we ever run into that instance?
So listen, what did we see about the XOR? What was the optimal minimal depth? Log of n, right?
Yeah.
2 log of n or order log of n. So the depth of the network depends on the dimensionality of the input. But typically when you design your networks, are you considering the dimensionality of the input when you consider the depth?
Probably not.
Exactly, right? So you always have a hard bound on the depth of the network.
Sorry, can you say that one more time?
So you always have a hard bound on the depth of the network. You're going to go and
Oh,
say,
I see.
correct? I may have 1,000 layers, but still there's a hard bound, and they're going to use the 1,000 layers regardless of the dimensionality of the input. So we always work in a regime where the depth of the network is decoupled from the dimensionality of the input. That's going to work just fine if for inputs of low enough dimension. So if you have a depth of say k, then if the input dimensionality is greater than 2 raised to k, you have a problem.
I see. Well, thank you.
Make sense?
Yes, it does, really. Thank you.
Hi, professors. Can I ask a quick questions about the circle decision boundaries?
Yeah.
Can you return back to the related slides? Yeah. This is I think the circle decision boundary.
Here.
So you're saying that we can use only one layers to construct this one circle decision boundaries, and by stacking those circles to approximate a complex like polygons or something like that. But when you say you are doing this, what I think is, are you like using the AND to combine all of those circles? And if so, then how can you let those circles coexist in the graphs? I mean, only OR can reach that effects.
So no, so look, all I'm doing is this figure is only showing the sum of the outputs of these neurons, correct?
Sure, yeah.
Correct. So this is, so this guy would maybe form one cylinder. This guy forms another cylinder, right?
Yeah, yes.
If I sum all of them together, what's it going to look like? 2 cylinders.
Okay. Just the sum of the 2 cylinders.
That's it, right? Because this cylinder is this bunch of neurons produces n/2 inside the cylinder and 0 outside. This bunch of neurons produces n/2 inside this cylinder and 0 outside. If I sum their outputs, where you have this cylinder, this guy produces a 0. Where you have this cylinder, this guy produces a 0. So the sum is going to look like this, right?
Oh, I see your point. So if we so in the real case, if we want to construct this kind of circles, we cannot apply the infinite neuron. Do we? Only the finite number of neurons.
If you apply a finite number of neurons, you're always going to get this leaking at the edges, and then right, like these patterns.
Oh, okay, I see.
And so then the sum is not going to be 0 in the intermediate regions, right?
Yes.
It can actually be greater than n/2.
Oh, I see. Thank you.
Right?
So each cylinder, just to double check, is an infinite amount of neurons.
Basically.
Thank you.
I mean, if you get to a very large number as the number of neurons increases, the area in which the value lies between n/n and n/2 keeps decreasing with n increasing n. So we can have a large number of neurons. The point is, it's an absurd number.
And like the circles can overlap, right? Like the region of their
if the circles overlap, in that overlap region is going to become greater than n/2. It doesn't really matter if you're slicing at n/2, right?
Okay, I see. Thank you.
Right.
I had a quick question on the thresholds on the slide that has the two cylinders. Yeah, here. So why is it that the threshold would be n over 2 and not n over 4 for each of those
No,
cylinders?
so I've used n neurons to compose the first cylinder and n neurons to compose the second cylinder.
Okay.
Right? So this is not n. N is the number for each cylinder.
Okay, I see.
Again, the concept is important, right? Yeah, that it's a very large number.
Thank you.
Can I have a question, Professor?
Yeah.
So when we are talking about the capacity of our network, we see that when we are changing the activation function from threshold to say ReLU, we decrease the number of neurons by half, right? So
Yeah.
does that mean like the graded functions can retain two dimensions of information, whereas the threshold can only retain one dimension of information? Is that correct?
Something like that. The threshold is basically going to tell you which side you are at, right? So this the threshold is basically 1 bit, whereas if you have a graded function, it's infinite bits of information.
Okay, thank you.
Okay, guys, I've got to be going to my next
All right.
class. I have to stop the recording. I never stopped recording.